Okay, so in this video, we're going to look at the properties of motion, and I'm going to show you some examples that you should be able to deal with if you have fully understood the concepts from GCSE physics. So the two times I'd suggest this video might be useful to you is at the end of GCSEs when you think you understand all the material, or at the start of A-level physics to make sure you have a good understanding of the aspects involved. So just a warning, I'm going to be using some obscure units for speed, acceleration, and distance. That does not affect your ability to do these. You do not need to know how to convert from like miles to inches or miles to meters or anything like that. The only conversions you'd be expected to be able to do will be between units of time in this. So between seconds, hours, minutes, that kind of thing. So don't be put off by the miles and inches as part of the questions. They're there just to make sure these questions look different to something you've seen before. Okay, so let's get started. So with each question, what I'm going to do is I'm going to pose you the question, and then with each one you should pause it, come up with what you think the answer is, and then we'll review it afterwards to see how well you've understood it. So first question, you're going on a bicycle ride. You ride at 1 hour, for 1 hour at 5 miles per hour, 3 hours at 4 miles per hour, and 2 hours at 7 miles per hour. How many miles did you ride? So these are your options, so pause the video and have a look through, and then we'll see what you get. Okay, so I'm assuming you've paused the video and solved this question. Let's now have a look at what you should have. So there are two ways essentially you can approach this question. One of them, which I prefer because it uses you can actually see what's going on, is I draw a graph. The other way is you can solve this using an equation. So first of all, the graphical method, you should know that distance traveled is the area under a speed versus time graph. That's something you should just know from the course. And this is what the graph looks like because it's at constant speed in each of the sections. So the area is just going to be adding together 3 rectangles. So 5 times 1 plus 3 times 4 plus 2 times 7 gives you 31 miles. The other thing you can do is if speed is constant, we have this equation, speed equals distance over time, and that equation comes from the fact that the graph looks like this. So if we rearrange that to make distance the subject, and we'll add together the 3 distances, so 5 times 1, 4 times 3, 7 times 2, and that gives us a total distance, again, of 31 miles. So either of these methods work, but I think the graph method is better because it puts it in a form that your mind can process more effectively in the form of a diagram. Okay, so let's have a look at the next question. So we're going to stick with the same graph, and what I'm going to get you to do is draw a distance versus time graph for this scenario we have just looked at. So again, pause the video, have a go at sketching this graph. Don't worry about being too accurate with it, but let's have a sketch. All right, so if we have a look at this one. So first of all, the thing you should know, speed is the gradient of a distance versus time graph. So in the first section, the gradient should be 5 miles per hour. So you've seen a straight line section because the speed is constant throughout up until essentially 1 hour has passed when it has traveled 5 miles. During the next section, it's going only at 4 miles per hour. So that should give you a shallower gradient like you can see on my graph. And it does that for another 12 miles, so the total distance traveled will be 17 miles at this point. The final section is 7 miles per hour, so that should be the steepest gradient on your graph, and the gradient would be 7 miles per hour, taking you up to a total of 31 miles distance there. So that's how you construct the graph, by thinking about the gradient and the speed. Okay, so let's have a look at a different scenario. So we've got a dragster, a car designed for going at very fast speeds in straight lines, and then usually use a parachute to slow down. So it's accelerating to 60 miles per hour from rest or 0 in 10 seconds. How far does it travel during those 10 seconds, assuming acceleration is constant? So again, I'd like you to have a go at solving this question, and then we'll go through it in a second. Okay, so now you've had a chance to pause and have a crack. Let's have a look at this one. Okay, so my starting point for this one was just like last time, sketching a graph of what the scenario looks like. So we're going from 0 to 60 in 10 seconds. And because acceleration is constant, that means the gradient is constant, so it's a straight line graph. So that's why it looks like a triangle. So you should know distance is the area under this graph. Again, this time the area is a triangle, which is why we've got half times base times height. So the interesting part of this question is figuring out how we convert from and get an answer in just miles, because we've got a speed in miles per hour and we've got a time in seconds. So one option here is we could turn our time into hours by dividing by 3,600, which you can see there. Or the other thing we could do is convert miles per hour into miles per second. Again, that would allow us to multiply them together and get a distance in miles. So if you look down the bottom left, so if you travel 1 mile per second, that means you would travel 3,600 miles in 1 hour, because it's 1 times 60 times 60. So what I do is I rearrange that to make the 1 the subject, because we should know that if we multiply an equation by 1, it doesn't change anything. So we want to convert miles per hour into miles per second, which is why I flipped it over to get the 1 over 3,600 miles per second divided by miles per hour. So when I multiply that by miles per hour, that's going to leave me with miles per second. So you can see if we convert either the time or the speed, we end up with the same answer with dividing it by 3,600. And when we do that, essentially what we're going to end up with is we've got 5 times 1 over 60, which is 1 over 12 miles that we've traveled. Okay, so what we're going to have a look at next is the same dragster, but we're going to take away its speedometer, so we don't know how fast it's traveling, but at its maximum acceleration, it goes 1/10 of a mile in 10 seconds. What speed did it get up to in those 10 seconds? So again, pause, have a go, see how you do, and then we'll review it in a second. Okay, so just like always, I start this by drawing a graph. So again, we're going to assume the acceleration is constant. It's going to start from 0 and again end up at some speed that I've called s after 10 seconds. And we know the distance to travel is 1/10 of a mile. So the distance traveled will be the area under this graph. So what I've done is, because the speed is in miles per hour, I've again put the conversion factor 1 over 3,600 in there. We could have divided the 10 by 3,600, it doesn't matter where we put it. And we know that half times 10 times the speed times the conversion factor should be equal to 0.1 miles, or 1/10 of a mile, which we can rearrange to calculate what s is, and it turns out to be 72 miles per hour. Okay. So next one, a different scenario. So using this speed graph, how far is the object from its starting point at the end? So after its speed becomes 0 again, essentially. So we've got 3 options here. So I'll give you a chance to pause and have a think, and then we'll take a look at what the correct answer is. All right, so let's take a look. So the correct answer here is it finishes where it starts. Because it doesn't matter what our units of speed and time are, we can see that there's an equal amount of area above the time axis as there is below. So during the first 2 units of time, we can see we've gone 3 units in the positive direction, so 3 sets of area in the positive direction. After that, we've gone 3 equal areas in the negative direction. Therefore, you end up exactly where you start. Okay, so a different scenario again. So we've got 2 cyclists traveling at a constant speed of 10 miles per hour towards each other. And you might want to draw a diagram for this one so you can visualize it. So to start with, they are 20 miles apart, but cycling at 10 miles per hour. And we've got a bee that flies from the front wheel of one of the bikes at a uniform speed of 25 miles per hour towards the other bike. So the bike's going at 10, the bee flies at 25, so it goes ahead of the bike. It reaches the other bike and turns around and flies back to the other one. And it keeps repeating that process until it is squished when the 2 bikes collide. Oh, it's very sad. So how far does the bee travel until it gets squished? So I'll pause it now, or you should pause it now. And what you need to do is try and figure out how far it travels until it gets squished from the start. Okay, so let's take a look at this one, because this one, if you think about it correctly, is an incredibly simple question, but it's very easy to make it very complicated. So the way I approach solving this is I worked out how long it takes until the bikes collide, and then once you've got that, you multiply that by the speed of the bee, and that tells you how far it has traveled. So we know that they're 20 miles apart, and we know they're approaching each other at 20 miles per hour because each one is going at 10 in the opposite direction, so they approach each other at 20 miles an hour. So it takes them 1 hour to collide, and the bee will travel 25 miles in that hour. That's how we'd approach this question here. Okay, so let's take a look at the next one. So we've got a streetcar, which those of you not familiar with, you have these a lot more in cities in America and in other countries rather than the UK. But essentially, it's usually a tram-like thing. So it's usually on rails, but it also travels on the road. So it's traveling at 144 inches per second. I don't know why we've got a distance in inches, but why not? And a person is walking towards the front of the streetcar at 36 inches per second, and that's relative to the streetcar. So the streetcar is going at 144, the person inside it's walking at 36 inches per second. The person is eating a hot dog, which is entering their mouth at 2 inches per second. So that's kind of going backwards a little bit. And then ant on the hot dog is running away from the person's mouth at 1 inch per second. So the question is, how fast is the ant traveling? So I'll pause it now and have a crack at this one, and then we'll take a look at what you should have got. Okay, so now you've had a crack. So I've represented this again with a diagram, as I always do, to make it easier for your working memory to process. So we know the person is moving in the same direction as the streetcar, so their two speeds would add together. The hot dog is going in the opposite direction, so we subtract 2, and the ant is going in the same direction as the people, so we add 1. And therefore we end up with a speed of 179 inches per second, as the speed at which the ant is traveling. Okay, so next one. So a stone is thrown straight upwards, and at the top of its path, its velocity is momentarily 0. What is the acceleration at this point? And we're still using like inches, feet, and miles and stuff. So G in this system has a value of 32 feet per second squared, but it doesn't change how you think about this question. So try and not fuss about that too much. So pause it now and have a crack at this question. Okay, so then what we're going to do is have a look at how I solved this question. So in terms of how I thought about it, at the top of its path, it's stationary. And when you're stationary, air resistance equals 0 because you're not colliding with any air particles unless there's a very strong wind. So what that means is the only force acting on you is your weight force, which we can calculate using mg. And it doesn't matter what system of units we're in, weight force is equal to mg. And if weight force is mg, that means acceleration is just going to be g, because we divide force by mass to get acceleration. So we can see that acceleration is just going to be equal to g when you're at the top of your path, when you are stationary. So a lot of people get this wrong because in their head they mix up velocity and acceleration and think they have to have the same value. But just because velocity is 0 doesn't mean acceleration is 0. There are a lot of scenarios where that's not the case. Okay, so that finished off this video looking at a few scenarios using the properties of motion and the graphs. If you have any questions at this point, please feel free to comment on this video and let me know, and I'll come and get back to you with some answers to those. But thank you very much for taking the time to watch.